hopefully it picks up the audio. So this is the demo thing. And what I have is I have basically a bunch of ways to do a dot product and a matrix multiplication. So how many of y'all have heard of Cuda? I'm curious. Okay, cool. So most of y'all have. For those of y'all who haven't, Cuda is like basically how you do anything on an NVIDIA GPU. It's the programming language for an NVIDIA GPU, and it's in C++ specifically. Anything you use, like NumPy or something in Python, all the fast, or not NumPy, but CuPy, whatever. All the fast libraries utilizing the GPU probably use Cuda or Sickle with Sickle.
Yeah,
Oh, hit. Okay.
They don't use Sickle.
Nobody uses Sickle. Oh yeah, Sickle's slow. So yeah, you've probably used Cuda before. All right. So first thing is and also I'm gonna be doing this for like 40 minutes. We also have where's Vedant? Vedant's gonna talk about JEPA, and you're gonna talk about visualization. Yeah. So it'll be somewhat short, hopefully. For those of y'all who just came in, can y'all sign in real quick? Oh, wait, Reese, sign in.
I will right now.
Cool.
The signing will be in.
I always forget to do this, so thanks. All right, garbage dot product. So what is the, there we go.
Garbage stuff. What a great startup.
Do we love garbage dot product?
Garbage product.
Yeah. So, garbage dot product. So like, what is the best way to like do a dot product? Well, I mean, to do a dot product, you basically have two vectors of dimension d. And literally all you do is you multiply the values and then you add them up. So it would be these two values multiplied together, and then you just sum them all up. So like the easiest way is to have a for loop that goes over d, and it just does a matrix multiplication and adds each one to some cumulative sum. So that's like an easy way to do this. And that's like the first way you would probably think of implementing this. So that's the first kernel, garbage dot product.
I can't believe that's what you called it.
You're utilizing one thread.
But it's funny.
So the big thing about Cuda is you have 1,000 threads, and you want to utilize the 1,000 threads as much as possible. If you do a for loop, that's basically what a CPU would be doing as like one thread. Maybe it has a few cores, but you basically have like one thread that iterates through everything, and you have no parallelism. So what Cuda does is you can launch a bunch of threads to do these operations in parallel and have them talk to each other. So I have this code here which allows you to utilize this in Torch. So there's a lot of things here like, utilize float 16 and make this a module that can be loaded in. And if you're curious, you can look at the code more for how this is adapted to PyTorch. But basically, I have this function here, and this function takes in two tensors, A and B. It checks to make sure they're CUDA. It gets the size, so just the dimensionality, and some data types and contiguous. So one thing I'm doing is I'm making this contiguous. That means that it's in memory sequentially. It could be non-contiguous, where it's scattered all over the place. I don't feel like dealing with that, but you can if you want. It's a pain to do that because you can't.
It's optimize if it's not together.
Yeah, but it also takes time to make it contiguous.
Only because the CPU has to do that.
Yeah. So yeah,
If it's non-contiguous, it's more optimized.
Yes, because threads, if you want to run at the same time exactly, when we want to space out precisely how much that thread will be, so we'll be grabbing it in order because program can jump around.
Yeah, but it's also a pain. It's so annoying. So
then you have to manage where everything.
Yeah, you don't want to do that.
Yeah.
And then you allocate the output tensor, whatever. I just allocate it to zeros, and this is just a scalar in this case because it's a dot product, and then some other weird things. So the main thing happens over here. This is going to be where we launch what's called the Cuda kernel. That's what this mess down here looks like. It's actually, I don't know why they have so much crap on this, on the launch, but whatever. So what I'm doing is I'm allocating a grid and a block and the shared memory size. And I'll talk about all three of those later. But for now, there's this thing called a grid, blocks, and shared memory. And the block basically tells you how many threads you're going to allocate. I'm allocating one thread. And this is how you allocate it. You call this forward kernel function, which is just a function that you're defining. This is just the type name. So in C++, if you template it, you can just give it the template. This is the special Cuda launch kernel thing. Basically, you define a grid, you define a block. So a grid we'll get into. A block is how many threads you have. Shared memory, we'll get into that. And then stream, we won't talk about that. That's just, I forget what stream does, but I never use it. I don't think most people don't use it. So once you launch this, it basically calls this function for every thread. In this case, we have one thread. And what it takes in is all the inputs we give it. So it takes in the A tensor, the B tensor, the output, which is just the scalar, and the size, and that's everything I'm just passing in on the launch here. It also has some special variables called block index and thread index. So block index is defined by the grid. That is confusing. Block index is defined by the grid, and thread index is defined by the block. I don't know why I did that.
Sorry, what is T?
T is the type name. So that's like
Okay.
float 6. So like
Okay.
in PyTorch, you can cast float 16, float 32. That just, this allows you to cast it super easily.
But
I have some functions.
It's
over
behaving
here.
like a templated type.
Yeah, it's a templated function. That's all.
Okay, it's a templated function.
Yeah, that's normal C++.
Yeah.
What is not normal C++ are these native things here, the block index and the thread index. These are they are not used here at all. Literally, all we're doing is having one thread, call this function, and the function iterates over the dimensionality. So all of n, it just iterates over everything. It adds it to this output, which we defined earlier. And literally all it's doing is multiplying the two indices and adding it up, so dot product. Now, if we run this, we'll see it is super slow. Like if we run it in this case, it's actually not that bad. But this is only with dimensionality 128. If we run it on a higher dimensionality, it's way slower than the native dot product in PyTorch. Surprisingly not that much slower, but that's because you can only optimize the dot product so much. So yeah, this is all it's doing. It's just calling it and timing it. So basic CUDA code, one kernel launch, that's it. So one thing that I did wrong in this CUDA kernel was I was just accessing global memory. So the problem with accessing global memory is it's very slow. You want to access, you have this thing called HRAM, I think HBM, and you have SRAM. So SRAM is very small.
Yeah, high bandwidth.
Yeah, high bandwidth, but it's on each thread. HBM is very large. It's like whenever you hear, I have an A100, I have 80 gigs of RAM. Those 80 gigs are very slow, but it's a lot of space. So that's your HBM. The SRAM is what you don't hear about, and you have like 20 megabytes of that stuff. And that's what I mentioned here. So on like an A100, you have 20 megabytes of that, but it's very, very fast. So instead, we want to utilize that. So I changed the kernel. Everything's the same, except for this one thing. Instead of me adding directly to the output, so in this case, I was adding to the output. It is much faster to add to a local variable. So this is a variable on a thread, and then put that in the output. That's because I'm accessing the global memory one time, as opposed to n times. So it's much faster. If I go here, well, at least should be faster. I don't know if it's much faster. So if I call that, it's much faster. This is the baseline here. This was the old one, 543 nanoseconds, I think, and 188 nanoseconds for the new one by just accessing global memory one time. All right, so now we want to actually utilize CUDA. So to actually utilize CUDA, we basically want to split this up into multiple threads. Now, the dot product example isn't super good. The matrix multiplication example is where it gets a lot more efficient if you start using CUDA. It gets a little more efficient with, I mean, you can make it a lot more efficient, but it gets really strange with dot product. So what we can do is we can allocate one thread to each index. So we can we have n indices, and what we can do is we can allocate a thread for index 1, a thread for index 2, and a thread for index 3. And each thread can do one multiplication. So in this case, I have A is equal to 1, 2, 3, and B is equal to 4, 5, 6. So we can allocate 3 threads. One thread does the multiplication for 1 and 4. The second thread does the multiplication for 2 and 5, and the third thread does the multiplication for 3 and 6. And then we have to add them all up, and that's the slow part. The slow part is having them be added up into one location and then sent it off to the output. And we'll just do that with thread 0. So this is where the kernel gets, it starts to look like a kernel. So recall this is where we launch the kernel. Now the block size is, or the number of threads we're launching, the block size is now n. So we launch one thread for each part of the matrix that we're going to be, or for each part of the vectors that we're multiplying together. Another thing I do is allocate this shared memory. So shared memory is memory shared between the threads. In this case, I'm allocating basically n indices of shared memory, and all this is a vector. It's a vector that's shared between threads, and this is faster than HBM, so the 80 gigs of RAM you hear about, but it's slower than on-thread memory. I need to plug my computer in. No, don't die on me. Much better. All right, so the reason we're going to use this is that we can have one thread. So all the threads are going to write to the shared memory. They each have their own index location. So the first thread will multiply the two first elements and throw it in the first element of the shared memory. The second one will do the second index. The third one will do the third index, and so on. And then we're going to have thread 0 go ahead and sum them all. So the kernel launch is the exact same, except we change the block and the shared memory size. So here, this becomes important. Thread index x. You can have x, y, z, that's why it's got x, but thread index x is, so like I said, every thread calls this function, and the function has local variable, these local variables, block index and thread index. So if I'm thread 0 and I call this function, thread IADX is going to be 0 for me. But if I'm thread 1 and I call this function, it's going to be 1 in the, for this variable here. So this is a local variable for threads, and so is this. This here is just allocating the shared memory. Don't worry about that. Now, this is doing the multiplication. So we take the thread index, so the index of the thread, we index the A and B vectors. We multiply them together, and then we store that in shared memory on its index. We then have to sync the threads because we have to wait for all the threads to do their multiplication. And once they've done their multiplication, thread 0 can go through and sum them all up. So it sums them all up and throws it in the output. So this is like the most basic example of a actual kernel launch, if that all makes sense.
Do you have a GitHub that you like?
Yeah.
Share the code with?
You
Let me
have
see.
to Git commit.
What's that?
He has Git.
Oh, it's a Git. Oh, I didn't see
Oh, no, I do have a Git.
Yeah.
it.
Let me share that. Oh, that makes sense. There we go.
Awesome, thank you.
Really, you don't submit your code in zip files?
I should
Like,
submit it in
can you
zip
apply?
files. Yeah, so it's shared. Commissioner told me. But
Real quick, so
Dude, it
is
was
shared
insane.
mem the global variable?
no, so shared mem is this thing. This is how much shared memory you're going to allocate, and there's 3 things that are this is local to the threads, but not global. So output is global.
Right.
Shared mem is local to the threads, but not local to each individual thread. And then these variables here are local to each individual thread.
Yes.
So this is shared between all threads. The shared mem is.
I'm just a little bit confused because I don't see. Oh, sorry, that's your
Yeah.
side.
So it like doesn't. It's this is how you allocate it, which is just a mess. I'm gonna call it shared mem because this looks terrible. But yeah, it's allocated here. This is just a fancy way of me allocating it for any data type. Don't worry about the definition. I threw this off.
And is the sync threads function a Cuda?
Yeah. So that's a Cuda function, and what it does is it waits for all the threads in this block, and we only have one block. So it waits for all the threads to, basically all the threads are running this code, and all the threads stop at this point until all the threads meet that point, and then they continue running. So that's all sync threads does. And that's because if you don't have this, the some threads may not be done with their multiplication. So like if thread 0 finishes really early and thread 1 does not, then it'll start summing, and it'll look at thread 1's sum, or multiplication, but it's not done yet, so it'll get trashed. Yeah. Yeah, so that's why we have to have sync threads. So this is probably going to be slower, but
Oh, you don't like including race conditions in your.
dude, I love race conditions. That's literally all Cuda. That comes with it. So here I'm just calling it again, and if we look, it's actually not that much faster. I'm showing the thread example just to show how you would do something like this. This is not the most efficient code, obviously. Now we can make it. Well, I guess it's a little bit faster actually, on large vectors. So a problem is we have one thread doing the summing, so you don't want that. And what would be more desirable is if you had you can basically build a tree. So we're going to utilize warps to make a tree, and the idea is instead of one thread, so let's say we have 6 elements in our shared memory. Instead of having one thread add, so one thread would have to look at 1, and then add 2, and then add 3, 4, 5, and 6. Instead we can build a tree where thread 0, or thread 1, sums the first 2 elements, thread 3 sums the second 2 elements, and thread 5 sums 5 and 6. And these are done in parallel. And then you do this again, and thread, what is this? 0? Thread 0 sums these 2 elements, and thread 0 just takes, wait, that's wrong. GPT, what the hell? I just copy and paste this from GPT, but you get the idea. If this was 3, yeah, this one should be going over here. Yeah, I did it, I added it wrong. Alright, so this one should be going over here. The 7 should be going over here, not over here. So thread 0 sums 3 and 7, and thread 11, or thread 0 sums 3 and 7, and then thread 5 just takes 11. And then you have thread 0 do the rest of the summing. So instead of it taking a bunch of operations, it just takes 3. And you can imagine if you have a really large dimension, this becomes very useful.
See, I mean, they said they could do single digit addition, but they didn't make any claims about it.
True.
2 digits.
And you can utilize warps for this. So there's this thing called a warp, which is more of it's some weird low level thing that's done on the GPUs. And it's basically these low-level operations that can be done really fast on 32 threads. That's basically that's how you can think about a warp. Why 32? I don't. Do you know why 32? They just decided 32, and you can do operations really fast, like a sum on 32 threads where they pass information.
The register.
Oh, 32 is the
Because
registers.
32 is exactly on the register they have.
There you go.
on the chip. The reason why it works is because the register is double the amount of 16 what you will see on a regular Intel CPU. But the reason the register are super small is one of the reasons why it can only make 32 of them without having it becoming an issue with the
That makes sense. So it can pass information really fast between the 32 registers. Yeah.
Okay, I buy that.
Yeah, that makes a lot of
makes
sense. I didn't know, so that's cool. But
uses that. Nobody ever uses that. Because
Sync-
you just do write to it, you have to take it in and out every time. To get it from CPU to GPU is very hard enough.
no, it's not on the CPU.
No,
It's
no,
just
It's
GPU.
on the GPU.
Yeah.
But to get it from CPU to GPU to the register, it takes too long. You have to just live on the GPU. So
Yeah. This is just living on the GPU.
Yeah, it's good, but it's not good for big data.
It's a good operation to know.
It's
though.
great as well.
Yeah, it's a weird operation. It's an efficient way to sum 32 values.
Wait, where are you?
So I'll show it in a second. So it'll be the same kernel launch, except we're going to make this tree. And to do this tree, so everything's the same. The problem is the sum. So the sum is going to be to create this tree. And what this tree does is it calculates this warp index. So say we have 128 values. We're going to have 4 warps because it's 32 for warp 1, 32 for warp 2, 32 for warp 3, and 32 for warp 4. And the idea is within each warp, we're going to sum to the first thread. So for the first 32 values, we're going to create a mini tree, and that's what this part does. And the small tree basically sums all 32 elements it creates the tree that I showed before, and sums them all up to the first element. And the second one will do the same thing, except it'll do it to the 32nd element. And the third one will do the same thing, except it'll be in the 64th element, and so on. So we're going to end up with 4 accumulated elements: the 0th one, the 32nd one, the 64th, and the 96th one. Yeah, I think I got that right. Basically, we split up the vector into 32 or we split up the elements we want to sum into 32s, which is the warp.
You're
we
talking
sum
about
them in the
indices,
warp.
right?
Yeah.
Okay, yeah.
We sum them in the warp, and then we're gonna wait for all the threads to finish doing the warp sum, and then we have thread 0 just iterate and add up all the elements that are left over. So if we have 128 indices, this would have thread 0 go and do 4 sums. It would be the 0th element, 32nd element, then the 64th, and so on. So hopefully you can kind of visualize that, where we break it up into pieces, we do the sums in the pieces, and then we have one thread go and sum all those up. You can also have another warp in the last one, for the second part of the tree, the sum after the warp, but I didn't utilize that. So basically, sum within each warp, sum within each part of 32, and then sum all the 32 values together and put that in the output. This is weird. It's very weird, but basically you're just creating a tree to sum up faster so that you can utilize more than one thread at a time instead of just the 0th thread. And it should be faster, at least a little bit.
So does this require, like, so you do your multiplication.
Yeah.
Does this require you, for each thread, to write to the registers and then do the addition there, and then move back?
What's up?
So quick correction is, so the reason why the East works is because initially whatever data you have is get a CPU to get transferred to a GPU. And if you want to use the registers, data whatever you get on GPU is going to the register. So normally how they do is they will actually first have it done on just the regular non-register and then have whatever output they get put it on the register. That's why they add it because it's more efficient, because whatever output threads itself in, instead of passing it back to the CPU, they leave it on the register put it out and then pass it on. Does that make sense?
They're all, yeah, it's all done on the GPU though.
Yeah.
But yeah, this thing basically passes information between threads.
Yeah.
To sum it up, yeah.
But you're having to put on the registers to do the addition, right?
Yes, that's what it
Okay.
does, yeah. It's a more efficient way than just looping through it and
Yeah.
doing it yourself.
Makes
So
sense.
instead of you creating the tree manually,
Yeah.
well, this does, it's just a faster way of doing it between threads, though.
And the registers are also, it's
Y-
also,
yeah.
it also solves the issue of like managing memory. I
Yeah,
guess.
it does, yeah. It worries about all the register stuff.
Yeah.
I would definitely not want to worry about that.
Assembly code.
Okay, FPGA guy,
FPGA.
no.
Who is this? What?
We're doing FPGAs now.
So it's a little bit faster, than the old version we
Yeah,
had.
this is the first time I'm actually using the shit I learned in assembly.
Yeah, and there we go. All right,
Debugging has
dot
to be
products. I'm not
What?
no debugging. Debugging is looking at the output and praying.
Debugging CUDA?
Yeah.
Oh my god.
Actually, for CUDA, debugging as of right now, NVIDIA has not made a consumer debugging tool.
It's actually really bad.
So looking at assembly code is the only way to debug these
Yeah.
during the execution.
Yeah, debugging this was basically compiling and being like, the output's a little wrong here. I wonder if my indexing is right. Looks like it was. I just have to find out where.
There's no like print statements at all.
So there
There's
are
a-
print
there's-
statements,
There's a string. So the string
Yeah.
that you mentioned earlier is essentially a way of looking into
You
the
can
code.
use-
but it's terrible.
It's-
Like
it
you
stalls so
because
much.
there's 1,000 threads doing this at once, so
Oh, right,
you
yeah.
get 1,000 prints.
Yeah,
It's
you don't know where it's from.
Yeah.
it's usually not worth it to just to print and to look at the code. It's usually more worthwhile, from my experience, to look at the code
They're not fair.
than to
But usually-
try to debug it. Yeah, like you can't step through it.
Looking at the assembly
Just
code,
No, not the assembly. You think I use
I
assembly?
get it. It's totally doable.
that's
Yeah, but you're
cursed.
insane.
Do
Alright,
you
so-
actually, is that actually how you debug?
Yes. Well.
Dude, that's insane.
What the hell?
No,
That
I
is
mean,
crazy.
Dr. Matthews' code literally cannot be debugged any other way than just put output in, and now
Yeah.
it makes sense.
Debugging assembly
crazy,
code is
dude.
insane.
All right, so that's dot
You look
product
at all the move
with
statements and you
warps
see,
and
oh
stuff.
shit.
Is that all? Everyone good with dot product? That last part
That's
is
cursed.
kind of weird, but it's breaking it up and summing. Everyone good with that? All right. Matrix multiplication time. Dot product. We don't care about dot products.
Kernel go bird.
Colonel Gilbert.
Yeah, you can download my library. Pip install kernel go burr. Anyone? No? It's okay, it's bad. So
Are you not referencing your kernelgober.egg-info?
yeah, no, that's exactly what I'm doing. I should put it on Pip. I should make
Kernel?
it Pip
Because I'm like,
accessible.
no way you did that.
Colonel
I should do that.
Gilbert.
That'll be funny.
Colonel Gilbert.
Too bad it doesn't.
What if
There's
it's
no
already
enough
taken?
R's. I'll add another R.
What if it's already taken?
Yeah. So matrix multiplication is this is basically why you would write a kernel to make this really efficient, not to make a dot product efficient. So let's look at the code for that. So for a matrix multiplication, we actually have to utilize blocks, but we have to do the stupid trivial example. Come on, scroll. Okay, cool. This
Are
scroll.
you using tiling?
Yeah, we'll get there.
Okay, okay.
Yeah. No, I'm not using tiling. I'm just
There-
using 3 for loops. That's efficient. So, trivial example, 3 for loops. So if we have an n by d matrix multiplied by a m by d matrix, we can just iterate over it 3 times, or all 3 dimensions. So n, m, and multiply along d. So this is just the loop going over the A matrix. This is the one going over the B matrix. And this is going over the dimension, and it's just multiplying them and summing them up. This is how you would implement it in Python, probably. Nothing special, literally just 3 for loops. Matrix multiplication. And if we do this, it is absolutely terrible. So, does it make a noise? Yeah, it's absolutely terrible.
Are you running this locally, or is it?
Yeah. Yeah, this is all local. It's all on here.
Okay.
Well, I ran it all beforehand because if you try to compile everything, it takes like 20 minutes. Because I put in all the torch stuff, just so that you could use it if you wanted to use it for. The torch stuff was annoying to get set up. My kernels may not be fast, but the torch stuff is there. So yeah, this is like terrible comparatively speaking. So this is the base, and this is nanoseconds versus milliseconds. Pretty good. This kernel's very fast.
It's almost the same if you don't look at a unit.
True. So we yeah.
Why exactly is the reason that graphic cards do matrix multiplication faster?
It's because of I think it's because of the number of operations you can do in parallel. Like you can't do that with the CPU as efficient. Like you can't do 1,000 threads at once.
It has a lot more cores, which basically means you can launch way more threads.
It's also made made to do matrix multiplication. So it doesn't like
Computer
the threads are
graphics is
made-
essentially just
matrix
matrix
multiplication.
multiplication.
Yeah.
It's literally just a big parallel.
Yeah.
Yeah.
So it's useful.
Yeah, a bunch of small operations.
Yeah.
And you like each thread does a small operation. Yeah.
So
And-
each core is a lot less powerful. Like we were talking about, like the registers themselves are really small, right, compared to CPU. But for things like matrix, like very parallelizable things like matrix multiplications, it works really well.
Yeah, let me switch.
Think about like blue collar, white collar. Like a CPU is a white collar job. It's like really smart, but it's really gonna do like high level stuff. Low
Yeah.
level stuff. Give it to like some outsourcing to someone low level blue collar job. It's
That's
kind of a
very
big factor for like people doing easy tasks on it.
Basically, yeah.
See, I would have said something like an army versus like a good general. You know, like more politically correct.
Versus a good general.
Yeah, like
That's
I wouldn't.
fine,
I
that's
would
fine.
blue
Doesn't
collar,
matter.
white collar.
You got
splits.
weird names in CS in general.
What?
Might as well make the weirdest names in CS.
The weirdest name.
Yeah, you name things weird.
Oh yeah.
Yeah. All right, so you have these matrices A and B, and to parallelize this, we're going to use something called tiling. So what we're doing is we have, well, this is our output matrix. This is going to be n by d. This is going to be m by d. I think I have this m by d there. And what we currently have is we have one thread that takes this one, it multiplies this element, this element, this element, this element, this element, this element, sums it all up, throws it here, and then the thread moves on here, and it does these, and then it moves on here, and it does these. Oh, I moved down one. And we have one thread doing that. This is obviously parallelizable if we have one thread do these, and one thread do these here. So you can parallelize this pretty, it looks really parallelizable, because this operation here does not depend on this operation at all. So you can parallelize this, and we're going to use something called basically blocking or tiling, whatever you want to call it. And the idea is that we have 1,000 threads. We should use all 1,000, and we should basically have this sliding window across the output matrix. So if we have 1,000 threads, that's 32 by 32 threads. And we can have each thread so we can't have more than 1,000 threads. So we could do this all at once if we had more than 1,000 threads. We only have 1,000. So to do this, we're going to utilize blocks. And this first block here is going to it's going to have all these 1,000 threads do these operations. So this first thread here will do this operation. And in parallel, this thread over here will do this operation here. And all these threads will do it in parallel. And once they're all done, we can move the block over to the right once or down once, and we'll move it over here. So then we have all these 1,000 threads do this operation for this next tile or this next block. And yeah, it'll do this one, will do this one and this one. This thread will do this one and this one. So that's the idea. Basically, you have 1,000 threads at your disposal. How can you parallelize them as best as possible? And the idea is to tile the output matrix and allow the threads to work parallel on the tiles. So that's what the next kernel is. Let's go there. So mapmol 2, I think this is the next kernel. I may have skipped ahead. What did I do here? Oh, yeah. So, this was, if you do d-threads, so instead of doing the threads in a block, if you do the threads along the dimensionality, the problem, so if you have 1,000 threads, do it along the dimensionality, and you just iterate over the dimensionality, the problem is what we had before. It's not that much faster, and that's because you have to have the threads communicate with each other. It's much faster if you have all the threads do an independent operation, because then they don't have to communicate with each other. So instead of having it parallelize the dimensionality, you can parallelize the output, or the output matrix. Here's that's in dark mode. Here's another example if you can kind of see. Oh, cool. It actually looks pretty good. You have this block. It looks a lot worse over here. It looks better up there. What? What are you laughing at? Oh, whatever.
Yeah, I can't read it.
What I showed before.
Browser.
The browser? What?
It's because it's like black text on a black screen.
It's fine. I don't want to change it from dark mode. I have to go to like settings or something. It's the example I just showed. So this one here is just parallelizing the dimension. It's bad because you have to have threads communicate with each other to sum up the dimension. It's more efficient if you have each thread do each individual dot product. And what we need to do is we need to allocate a block. So this defines how many blocks we want. If we have a 32 by 32 block size, then we want to have n divided by 32 by m divided by 32. So that's just our block that we're going to be working with. Because our output matrix is n by m, you want to tile that n by m matrix, that n by m matrix. So this is how many blocks we have. That's our grid. Block is the block size. So our block size is 32 by 32, and we're not going to utilize any shared memory. And yeah, this is just launching it, but it passes in n, m, and d instead of just d, like we did with the dot product. So it scrolls up. Why aren't you scrolling? Scroll. So here, I define the block size, and then I define the block index on x and the block index on y. So the block index on x is just the index multiplied by the size. So this is so each thread calls this, and each thread wants to know what part of the output matrix it wants to work with. So you need x and y coordinates, and that tells it where the output is going to be stored. These here are the index within the block. So, yes, these are the thread indices. So this tells it where it's going to be working inside its block of threads, and this allows you to calculate the global thread index. These are the x and y coordinates. This is the coordinate for the A matrix, and this is the coordinate for the B matrix, and this is the global xy coordinates that you're going to be working with. So all you're doing is you're telling the thread which part of the matrix are you going to sum for your A matrix, which part of the matrix are you going to do the dot product for the B matrix, and where are you going to store that. And those are the definitions, and you can define that all locally. And literally all you do is you iterate, since it knows which parts it needs to do the dot product with, you just do a dot product, and then you store it where you said you wanted, where that thread is supposed to store it. So it's pretty simple, and it does what we would expect. It tiles it, all the threads do what we want them to do, and it's a lot faster. It's 78 compared to 15. Oh no, one is that 191? Yeah, 191. That's much better than 15 milliseconds. 191 microseconds, I think, or nanoseconds. I don't. What's mu? Is that nano?
Yeah, it's micro.
Micro. Okay, cool.
Micro.
I'm not an ACE. I'm not an exponential now. I don't know my units. So yeah, that hopefully this makes sense. Tiling. Everyone good with tiling? Anyone got any questions with tiling? Cool. It's basically what's used to actually implement this. One thing I wanted to show, which didn't make it that much faster, is you can utilize shared memory to have the threads load in memory beforehand. So let me show that real quick, and this will be the last thing I show. So if you have threads here, so this we'll go with this part. So some block in the middle. And this block is going to utilize these two parts of the A and B matrix. So what each thread has to do is each thread has to load these parts of global memory, and then it sums them. But this part of global memory is utilized by all these threads here. So instead what you can do is you can have, like, this thread load parts of this into local memory, into the shared memory, and then this thread load in maybe these parts over here. So different parts of the global memory into shared memory. And you do that before you do the computation. And that way, if you load it from global memory to shared memory beforehand, it has to you access global memory a lot less. So it can be a lot faster if you have to access global memory a lot more times. In this case, it wasn't that much faster, but I know it's used sometimes to load global memory into local memory between threads, and then utilize that instead of having it access global memory a lot. So here is where I'm doing that. Each thread basically loads a part of it, and I just divide the dimensionality by the block size essentially, and that way the threads all load in a part of the dimensionality uniquely, and like I showed before, where one thread will do like every 32nd, one thread will do every 32nd plus one, something like that. And then it utilizes the shared memory instead of the global. Like I said, it didn't make it that much faster, but I know this idea is used other places. It actually made it slower there. It actually made it slower here. Whatever. It's faster sometimes, not in this case, but the main idea is the tiling that you want to do for each matrix. Just this idea is used for other things, the preload before you preload into shared memory. So yeah, Cuda kernels. That's all I got. Matrix multiplications. Hopefully you know a little bit more about Cuda, and I guess you hate yourself a little bit more because coding in Cuda sucks. Also, floating 16 works.
Whoa.
Cool. Cuda sucks.
There's worse ones. Hip? Sickle? I think there's worse.
Not dealing with
What's
that.
hip?
Oh,
It's not hip.
What's hip?
It sucks.
hip is absolutely
What is
You
hip?
can actually just run like the hello world program, and your computer will turn off. It's
So-
garbage.
Oh yeah, I've crashed my computer a few times with Cuda. If you,
Yeah, you can do
yeah,
that.
pretty fun.
What is hip?
HIP is like a different
AMD's
AMD's
Cuda.
version of